Let's now consider this problem. For probability, a die is rolled 30 times. Let x be the number of aces that appear. Find the probability that x is equal to 3. The expected value of x is expected value of x, and the standard deviation of x. The first thing that we notice is that this is a binomial experiment. There are 5 things that we worry about for a binomial experiment. There are a fixed number of trials. There are 30 trials. The trials are independent because rolling dice over and over again are independent events. There's only one defined outcome, success, where I'd roll a 1, an ace. So rolling a 1 or an ace is success. Rolling something else is failure. The probability of success each time is the same, 1/6. And the central problem is counting the number of successes, so counting the number of ones that appear. So this follows the binomial distribution, and so we know that the probability that x is equal to 3, using the notation used in the text as well as in class, this will be equal to b 3 with parameters 30, the number of trials, as well as the probability of success in any one single trial, which is 1/6. So this is equal to 30 choose 3 times 1/6 to the third power times 1 minus a sixth, which is 5/6, to the 30 minus 3. So 30 minus 3 is 27. So the exponent 3 denotes the number of successes. The exponent 27 denotes 30 minus 3, the number of failures. 1/6 of the probability of success, 5/6 is the probability of failure, and I multiply by this combinatorial coefficient 30 choose 3 for the number of ways that you could get 3 successes in 30 trials. Okay, 30 choose 3, that's equal to 30 factorial divided by 3 factorial times 27 factorial. Again, times 1/6 to the third power times 5/6 to the 27th power. (30 factorial, that's 30 times 29 times 28 times 27 and so on down the line. So 28 times 27 factorial, 27 down to 1. Divided by 3 factorial, the definition of 3 factorial is 3 times 2 times 1. And then I've got a 27 factorial here, so I get 27 factorial 1 times 1/6 to the third times 5/6 to the 27th power. Okay, now clearly we can do some cancellation here. So 27 through 1 cancels top and bottom. 3 times 2 is 6, so that goes into 35 times. And so what's left is going to be 5 times 29 times 28, which is 4,060. Times 1/6 to the third times 5/6 to the 27th. And as noted in class, the number 4,060 that we see here, there's a few ways this can be obtained. You can obtain this through factorials, like we did here. This also is the 30th row, third column of Pascal's triangle. Remember to count by zeros. So you start the count on 0 for the top row and the initial column. There also is a button on the TI calculator that will compute this binomial coefficient for you, which was discussed in class. You can go to the, I believe, statistics menu, and then hit probability to get to the NCR button. If you have any difficulties finding such a button on a calculator, feel free to ask me. And then finally, 4,060 times 1/6 raised to the third power times 5/6 raised to the 27th power, just plugging that into my calculator that I have on my desk here, we get the answer of 0.1368. Accurate to 4 decimal places. Okay, next let's figure out the expected value of x and the standard deviation of x. The first way of figuring out the expected value of x would be to find all the possible values and the probabilities for each. Well, the possible values of x are 0, 1, 2, 3, 4, all the way up to 30. And then we do a calculation like we just did to figure out the probabilities. Then we multiply and add them up, and that's our expected value. Now, I'm not writing that out because that is the wrong way to do it. We have a shortcut method for the binomial distribution that gives us the expected value. Now, this formula only works when I have a binomial random variable that the expected value of x is equal to n times p. So in our case, that's equal to 30 times a sixth, which is 5. And this you probably could have gotten before ever taking the course. If you roll a die 30 times, you expect to get 5 ones. Kind of makes sense. Standard deviation of x. This you probably could not have gotten before taking this class. The formula, again, this formula only works if I have a binomial random variable, the square root of n times p times q. So square root of 30 times 1/6 times 5/6. And then plugging that into the calculator, that's approximately equal to 2.0412, accurate to 4 decimal places. So if I roll a die 30 times, I expect to get 5 ones, 5 aces, give or take 2 or so. If I get 7 aces, I'm not surprised. If I get 12 aces, I am surprised because that'd be 7 more than expected, or about 3.5 standard deviations. So this is a way of quickly characterizing the central value as well as how spread out the data can be about that central value.